All right, guys, so I'm going to go over the Unit 6 Progress Check, MCQ, and FRQ today. Now, a bell may ring in the middle of this, so just be prepared. It probably will ring in about 20 minutes, so just be prepared for that. So number 1 says the chemical reaction between hydrochloric acid and ammonia is represented above. A student combines equimolar amounts of hydrochloric acid and ammonia in both solutions initially at 24 degrees Celsius in a coffee cup calorimeter. The student observes that the mixture reaches a temperature of 28 degrees Celsius. Based on the experimental results, which of the following can be concluded about the reaction? So let's look at it. So both solutions started initially at 24 degrees Celsius, but then what happened was the temperature increased to 28 degrees Celsius. What that tells us is that if the temperature increased, that means heat is being released by the reaction, and that is an exothermic reaction. So A and B are not correct. And then D, it says it's an exothermic process because energy is absorbed by the reaction. That is not true. What happens is that energy is released by the reaction. And what actually happens is that energy is released by the reaction. What actually happens is that energy is absorbed by the surroundings but is released by the reaction. Okay. Now, number 2, it says when pellets of sodium hydroxide are added to a flask of water, it is observed that the temperature of the water increases as the pellets dissolve. Which of the following claims about the observed dissolution of sodium hydroxide in water is most accurate? So what's happening is the sodium hydroxide is dissolving in water, and the temperature increases. So that tells me that the reaction is releasing energy. So it's exothermic. So A and B, again, are not going to be correct. Now let's look at C and D. These are worded differently, so you got to be careful. It says it is an exothermic process because heat energy is absorbed by the water as the sodium hydroxide dissolved it. And then D says it is an exothermic process because heat energy is released by the water as sodium hydroxide dissolves it. So what happens is we know that energy is released by the reaction, but since the water is surroundings, the heat energy is actually going to be absorbed by the water. So you got to pay attention to what's happening. Remember, the reaction is the system, and then the surroundings is everything the system is. In this case, it's the water. And so heat energy is being absorbed by the water, therefore it means it's released by the reaction. Now, number 3 says an advertisement for a commercial hand warmer claims that the hand warmer works because a chemical reaction in the hand warmer draws out the body's own natural heat, causing a warming effect. Which of the following statements of accuracy in the claim is in the advertisements best provides a correct scientific justification for the claim? So what happens is this hand warmer says that it draws out the body's natural heat, causing a warming effect. Now, one thing we know what happens is if heat is being drawn out of anything, if it is being taken out of anything, it actually causes things to get cooler. It causes a cooler feel, right? So if heat is being absorbed by the hand warmer, then that means it's going to cause your hands to feel cold instead of hot. And so the correct answer here is the advertisement's claim is inaccurate because heat flowing from the hands to the warmer would only happen if the chemical reaction was endothermic, which would cause the hands to feel colder. Now, number 4, it says a student carefully drops 9 grams of zinc pellet initially at 50 degrees Celsius into an insulated cup containing 30 grams of water at 27.8 degrees Celsius. The student predicts that the temperature of the water will increase after the pellet is added. Which of the following statements is best justification for the student's prediction? So he predicts that at 50 degrees Celsius, I put in zinc and water, that is 27.8 degrees Celsius. And he predicts that the temperature of the water will increase. Now, remember what happens with heat transfer. So heat is always transferred from the hottest to the coldest. So heat's going to be transferred from the zinc to the water. That is going to cause the water's temperature to increase, but we want to know why. Now, in A, it's talking about metallic bonds between zinc atoms will break when the zinc is exposed to water molecules. That is not happening. A reaction is not happening. It's just a heat transfer, so A is not right. C says the strength of the hydrogen bonds between water molecules will increase when a zinc pellet is added, decreasing the average kinetic energy of the molecules. Heat transfer has nothing to do with hydrogen bonds. Now, collisions between zinc atoms in the solid will increase the frequency when zinc is exposed to water molecules, resulting in a transfer energy to the surroundings. Now, the collisions between the zinc atoms is not what's happening here. It's collision between the zinc atoms and the water. And so D is not correct either. So B says collisions between water molecules and the surface of the zinc pellet will result in transfer of energy, increasing the average kinetic energy of the water molecules. And that is true. So what's happening is heat's being transferred from zinc to water, and therefore that's increasing the average kinetic energy of that water. Okay, number 5, it says 2 aqueous solutions of sodium chloride of equal volume and concentration were kept in flasks and held at different temperatures. The 2 solutions were combined in a larger flask. Based on the information, which of the following predictions is correct? So 2 different sodium chlorides, one was, say, warmer and one was colder because they were at 2 different temperatures, and then they were mixed. So we need to see what these different things are proving. Now the answer here is B. The average kinetic energy of the particles in the cooler solution will increase as they collide with the particles from the warmer. And that just defines that, remember that the average kinetic heat flows from warm to cool. So heat will always, the warm will always warm up the cool will never warm up the warm. And so that causes the particles of the warm to move faster. All right, number 6 says a table provides data for 2 CH3OH samples. Based on this information, which of the following statements describes what happens when the samples are initially mixed and why? So we have 2 samples of methanol. That's what CH3OH is. And we see that there are 2 different volumes, okay, and 2 different temperatures. So we have one at volume 1 at initial volume of 125, temperature of 36 degrees Celsius, and 2 is initial volume of 250 at 18 degrees Celsius. So what we can know is that, remember that temperature flows from warm to cold, same with thermal energy. So the answer is going to be D. It says the methanol molecules from sample 1 transfer thermal energy to the methanol molecules from sample 2 through collisions because the average kinetic energy of the molecules in sample 1 is greater. If the temperature is greater, the average kinetic energy is greater, okay? And so what's going to happen is that it's going to go from a greater average kinetic energy to a smaller average kinetic energy. So just how heat flows from warmer to cooler, average kinetic energy means that it's going to flow from a greater average kinetic energy to a smaller average kinetic energy. All right, number 7 says the graph above shows the changes in temperature recorded for 2 liters of water surrounding a constant volume and container, which a 1 gram sample of benzoic acid is combusted. Assume that the heat was not absorbed by the container or lost by the surroundings. The density of water is 1 gram per milliliter, and the specific heat capacity of water is 4.2 joules per grams degrees Celsius. Based on this information, estimate how much was released from the combustion of benzoic acid sample. Okay, so we have 2 liters of water and a 1 gram sample of benzoic acid, and we're asking how much heat was released from the combustion of benzoic acid. So we're going to use Q equals mass times specific heat times the change in temp. Now this is the mass of the water. So we're looking at how benzoic acid affected the water. And so this is the mass of the water. Now we're given 2 liters of water. Okay, and our density is given in 1 gram per milliliter. So we want to first convert the liters to milliliters. So 1 liter, there's 1,000 milliliters. And then we want to convert milliliters to grams using the density. In 1 milliliter, there's 1 gram. Okay? And so what we'll get is 2,000 grams of water for our mass. So we get Q equals 2,000 grams times 4.2 joules per grams degrees Celsius. Now times the change in temp. So we got to look at our graph to find the change in temp. So I see here it starts at about 24.9, sorry, not 24.9, 22.1 degrees Celsius, and then it ends up at about 24.9. And so what we're going to do here is we're going to do final minus initial, so that's 24.9 minus 22.1. And so when we plug that in, we get Q equals 23,520 joules. Okay, notice the unit is in joules because the specific heat was in joules, okay? Now, but my answers are all in kilojoules. So to convert joules to kilojoules, we divide by 1,000, okay? And that will give me 23.52 kilojoules. And the closest answer I can see for that would be B, 25 kilojoules. Okay, now number 8, it says, for an experiment, 20-gram piece of aluminum was placed inside an insulated cup with 40 grams of water. The data are given in the table above. Assuming no heat is absorbed by the container or the surroundings, which of the following equations best provides the correct mathematical relationship for the transfer of heat between the aluminum and the water? Okay, so notice that it's the initial transfer of heat between aluminum and water. The heat transfer is not, the initial heat transfer, or this heat, just heat, is not dependent on the amount that we have. Because remember, just it doesn't matter how much of each, the heat that's from the aluminum will always transfer to the water. And so the answer is going to be D. Now these with the 2 and the 6 and the 12, that has to do with delta H, the heat of the reaction. Remember, the heat of the reaction is stoichiometrically related. But this is not. Okay. All right, so number 9. It says a student dissolves 8 grams of NH4NO3, so that's ammonium nitrate, and 100 grams of water in a coffee cup calorimeter. Based on the initial and final temperatures of the mixture in degrees Celsius shown in the diagram above in the laboratory setup, what is the calculated delta T of the water reported to the appropriate number of significant figures? Okay, so this is actually a sig fig thing. Now, when measuring, you can only predict one significant figure. So here, have actual lines. Those are not predicted. Now, the lines in between are the predicted. And so what's happening here is I have, I see my initial temperature was 25.5. Sorry, y'all.
Mr. Hutchinson and Miss O'Hara, you guys have packages in the front office.
So our initial temperature was 25.5 degrees Celsius. And then our final temperature was 20 degrees Celsius, okay? So final minus initial would be 20 degrees Celsius minus 25.5 degrees Celsius, and that will give me negative 5.5. Now, sig figs here, again, remember, this second, this 0.5 here was predicted, because notice here, let me erase it. Notice that there are no lines where that 0.5 was predicted. So you can only have one predicted place on a significant figure.
Coach Brady,
sorry, y'all.
Miss Farrington, and Miss Ainsworth, you guys also have packages in the front office.
Okay, number 10. It says particulate models of the evaporation of liquid water and the condensation of water vapor are shown above. Based on these models, which of the following accurately compares the energy changes associated with each phase change? So we have evaporation. So remember that it's the evaporation absorbed enough energy to break free from the liquid, and then condensation absorbed enough energy to condense back into it. Now notice here we got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I have 7 water molecules evaporating and 7 water molecules condensing. That is a 1-to-1 ratio. So the amount or so C is going to be the answer. It says the amount of energy absorbed by 1 mole of water molecules as they escape the liquid is equal to the amount of energy released by 1 mole of water molecules as they come together to form a liquid. Okay. Now, my next one, number 11. It says in the table above provides the values for some physical properties of sulfuric acid in water. Approximately how many moles of sulfuric acid must be condensed to release as much heat as would be condensed or released when 1 mole of water is condensed? So here we have our heat of vaporization. Okay, 1 mole of water takes 40 kilojoules for heat of vaporization. Now remember, the opposite of heat of vaporization would be heat of condensation, and it's just a negative. So this would be negative 40 to condense, and this would be negative 20 to condense. So if 1 mole of water takes negative or releases negative 40 kilojoules to condense, then 2 moles of sulfuric acid will have to release negative 20 kilojoules each to get a total of negative 40 kilojoules. And so the answer is going to be 2. Now, number 12, it says the heating curve for 1 mole of sodium initially at 25 degrees Celsius is shown in the table to the left. Which of the following best explains the change in heat when 0.5 moles of sodium undergoes the transition shown in the diagram above to the right? So here's a heating curve, okay? And this is for, the heating curve is for 1 mole of sodium. Now what's happening here? Sodium is going from a liquid to a gas. And I can see that because the liquid, they're a little bit far apart where this will kind of together, whereas a gas, they're all spread throughout the container. Okay, so that's what's happening here. Now in my heating curve, remember, any flat part of the heating curve is going to be when it is transitioning from a solid to a liquid or a liquid to a gas. In this case, it's a liquid to a gas. So we start at 30 kilojoules and we end at about 229, okay? So we start at 30 kilojoules and we end at 129 kilojoules, okay? So to find how much kilojoules it took, we do 129 minus 30, and it took 99 kilojoules for that to happen, okay? For 1 mole of sodium to go from a liquid to a gas, it took 99 kilojoules. Now, but look what it's asking. It says Bex explains the heat when half a mole of sodium is. So if we are doing half a mole, it's going to take half as much energy, and so we would do 99 divided by 2. And that would give you 49.5. It would take 49.5 kilojoules for half a mole to undergo this transition. And so the answer is going to be B. Now, number 13, it says the enthalpy change for the reaction represented by the chemical equation shown above is delta H equals negative 1236 kilojoules per mole. When 2 mole of NaOCl reacts completely with excess of Na2S2O3 and of NaOH, which of the following enthalpy changes occurs? Okay, so according to my reaction, if I have 4 moles of NaOCl, then it will take negative 1236, okay? But in this case, I have 2 moles of NaO6, and so so what we do is we have half the amount of moles, so that means it's going to take half the amount of energy, and so that's 618. Now, the 618 is, it's going to half, or the delta H of the reaction is going to half to negative 618 kilojoules, and so the answer is going to be C. Now, number 14, it says the chemical equation shown above represents the thermite reaction. What is the approximate amount of heat released when 108 grams of aluminum reacts with excess iron oxide? Okay. So first we're having 108 grams of aluminum, okay? And I want to know how many moles of aluminum I have reacting, okay? So I'm going to divide by molar mass. And that's going to give me 4 moles of aluminum. So I have 4 moles of aluminum reacting, okay? Now in 2 moles, I have 2 moles of aluminum in the reaction, but 4 moles are actually reacting, or 4 moles here reacting. And so since I double the moles, I double the delta H. And so I'll do 850 times 2, and that will give me 1700. That's where D is coming from. Now, number 15. It says the equation shown above represents an endothermic reaction between carbon monoxide and carbon. What is the amount of heat absorbed when 1 mole of carbon monoxide reacts with excess carbon? So in my reaction I have 2 moles, but here I have 1 mole. And so I'm going to take the delta H in this case and divide by 2. So when I would do 127.3 divided by 2, I'm going to get that 63.7. Now 16, I can't tell y'all how many times I've actually worked 16 out. I have no idea why the answer is 300. Every time I work it out, I get 600. So I'm just going to have to consult with Ms. Shoemaker and just kind of see if there's anything that I'm missing here. But as of right now, we're just going to skip over that. Okay. Number 17 says the combustion of methane proceeds according to the chemical reaction. The table above provides the average bond enthalpy for selected bonds. The calculated enthalpy change of the reaction is delta H of the reaction is negative 802 kilojoules per mole. Which of the following provides the mathematical procedure to estimate the bond enthalpy per mole of O2? So in my reaction, I have 2 moles of O2, but if I want to do per mole of O2, that means I'm going to have to multiply everything by 1/2, okay? And so that's why A is the correct answer, because it's 1/2, and then negative 8.2, that's the delta H of the reaction, and then 2 times 799 plus 4 times 464, both of those are our products. And then minus 4 times 414, that is our reactant of methane. Now number 18, it says the formation of hydrogen chloride gas is represented by the chemical equation H2 plus Cl2 yields 2HCl. Based on the bond enthalpy data in the table above, what is the appropriate or approximate enthalpy change for the reaction? So delta H of a reaction is, for bond enthalpy, is going to be the sum of the delta H's of the bonds broken plus the sum of the delta H of the bonds formed, okay? Now, in this case, what we want to do is we want to make sure that our bonds broken are positive and our bonds formed are negative. So our bonds broken are going to be, is going to be the H2 and the Cl2. Now, the H2, now notice that in this reaction, there's a coefficient of 1 for H2 and Cl2, but there is a coefficient of 2 for HCl. So you got to take those into account also. So H2, I have 1 H2 bond breaking, correct? Because I just have 1 H2 molecule. So that's going to be 436 kilojoules. Plus, and then I have 1 Cl2 bond because I have 1 Cl2 molecule. And so that's going to be 243 kilojoules. Okay. Plus, sorry, that should be, yeah, the sum, sorry. Plus the sum of the bonds formed. Now, I only have one type of bond being formed, but I have 2 of those bonds. I have 2 HCl's. So I have 2 HCl's, so I have 2 of these bonds forming. So you got to go 2. Now, in this case, bonds are being formed, which means energy is being released. And so that's going to be negative 432. Okay? And so when I put all those together, I get negative 185 kilojoules per mole. Okay. Now, number 19, calcium carbonate decomposes according to the balanced equation. Based on the standard enthalpies of formation provided in the table above, what is the approximate enthalpy change for the reaction? Now, in this case, we have heats of formation. We're not talking about bonds breaking or bonds forming. We're talking about heats of formation. And so what we want to do is we want to keep our formula is going to be delta H F equals the sum of N times delta H heats of formation for the products minus the sum times the number of moles times the heats of formation for the reactants, okay? Now, I may or may not have taught you wrong here, but give me 1 second, hold on. I want to double check this. Negative 640 plus negative 390. Okay, so because this, in this case, notice it's minus, because it's minus, that's going to help us kind of solve the positive, negative signs at the end of it. So you want to put the heats of formation as is. And so what we're going to do is we're going to put negative 640 plus negative 390 minus negative 1210. Okay, so this is the heats of formation of CaO and of CO2, and this is the heat of formation of CaCO3, okay? Now, notice I still kept it negative because it is minus. That minus kind of helps us, what it does is it's subtracting the amount of energy that is used to form CaCO3. Basically, it just, what it does is it equals out our positive and negative signs, and so in the end you'll end up getting the same amount as if you change the sign to plus. So we don't want to change this 1210 to a plus. We don't want to change that to a plus because of the minus sign. Okay? All right, number 20. It says, based on the information above, what is the heat of formation for the reaction SO2 plus 1/2 O2 yields SO3? So delta H, again, is we're gonna use the same formula as up here. The sum times the sum times the number of moles times the delta H. Sorry y'all, I haven't had my coffee this morning, so I'm kind of struggling here. So we're gonna use this, the sum in delta H of the products minus the sum in delta H of the reactant. So the products here is SO3, and so my delta H of SO3 is going to be negative 395.2. And I'm not going to multiply it by anything because the coefficient here is 1. And that's going to be minus negative 296.1. And one thing I want to point out, I don't think I was very clear about this. If I do minus negative, that's plus, and that's going to change that to a 296 anyway. And so that's going to take the difference of I have 395 forming, or 395 that's coming out of the formation of SO3, but 296 going into it. And so I have to subtract 296 from that 395 to get my net energy. And so when we do that, that's going to be negative 99.1 kilojoules per mole. Okay. Now, number 21, it says natural gas consists primarily of CH4, which is combusted according to the following equation. Based on the standard enthalpies of formation in the table above, which the following expression gives the approximate enthalpy change for the reaction. Okay, and so basically what it's asking is to correctly plug in this formula here. So correctly plug in this formula here. And so the answer is going to be C. Number 22 says that given the equations, the values of delta H for the combustion of C2H6 and the combustion of graphite represented above, which of the following additional information is needed to determine the values of delta H for the overall reaction? So we have our overall reaction is graphite, 2 graphites as our reactant, 3 hydrogens as our reactant, and 1 C2H6 as our product. Now let's look and see what we have in our reactions given. We have C2H6 as a reactant, and so what we can do is actually flip this reaction to where C2H8 is a product, right? We have carbon graphite as a, so we got that covered. We have carbon graphite as a reactant. We got that covered. So now what we need is 3 hydrogens as a reactant, okay? I'm trying to think. Oh, we would multiply this by 2 to get the 3 hydrogens. So one thing I want to point out is that we have CO2 and water as a reactant. And so the CO2 will cancel out here if it was a reactant with the CO2 here, the 2 CO2 there. But the 3 waters will not cancel out with this reaction that we have. So we also want water as a product, and we want hydrogen as a reactant. We want both of them to be 3. So the reaction that I could use would be this one: hydrogen as a reactant, water as a product, and then also oxygen to equal 7/2. And so we could take this reaction and multiply it by 3 to get what we need. Now, number 23, it says the enthalpy of the overall reaction represented above can be determined by adding the enthalpies of reactions 1 and 2, which the following could be reaction 2. So again, we have 2 O3s, 2 O3s, so we are good with that. But we don't have 2 NOs as our reactant. We have 3 O2s, and we have 2 O2s, okay? But we don't have 2 and 2 O2s as our product. And so we want a reaction that has NO2 or 2 NOs and 2 NO2s as our reactants and products, and then 1 more oxygen, because we want or an oxygen as a reactant over here, so it can mark out one of the oxygens to make it 2. Okay, and so our answer is going to be C. We got 2 NO as a reactant, 1 O2 as a reactant to mark out that 3 O2 to make 2 O2, and then 2 NO2 as our product. Okay. Number 24, it says the table above provides the values for the standard enthalpy change for 2 chemical reactions. A student needs to calculate the enthalpy change for the reaction 2H2O3 yields N2O5 plus H2O under standard conditions of using Hess's law. In addition to the values given in the table, what other information will the student need to perform the calculation? Okay, so here's our reaction. We need HNO3 in one of the reactions, which is here. We can flip that one, right? We need N2O5, but I don't see N2O5 in either of those, and we need water in one of those, and that's what this is here, formation of water. So one thing we need is also the delta H of N2O5 to calculate the delta H of the reaction. Okay. All right, so FRQ. So a student added a sample of ammonium nitrate to water to measure the temperature over time. The data are shown in the graph above. So notice what happens here. The temperature decreases. So that tells me that this is an endothermic reaction. It says, what is the value of delta T the student can use to calculate Q? So delta T is final minus initial. Now the initial was 24, that's 24.8, and the final was about 22.2. And so final 22.2 minus initial 24.8 will give us negative 2.6 degrees Celsius. So you can, it said on there that they would accept negative 2.6 or 2.6 degrees Celsius, either one. Now B, it says, according to the graph, the dissolution of NH4NO3 is endothermic or exothermic. Explain. So we said that it's endo because the temperature is decreasing, okay? Now it says the temperature is decreasing, and in endothermic reactions, temperature and energy of the system decreases, okay? Now C, it says, are the strengths of the interactions between the particles in the solute and between the particles in the solvent? So this is solute, that's the interactions of the particles between the solute, and the solvent reactions. Before the solute and solvent are combined are greater, less than, or equal to the strengths of the interactions between the solute particles and the solvent particles after they are combined. Now, this answer is what happens is the strength between the solute and the solvent particles are greater than the attraction of the solute. So when something dissolves, that means that the solute-solvent attraction is greater than the solute-solvent-solvent. But something can still dissolve if it's given enough energy. So what happens with endothermic, it's putting energy into breaking these bonds and forming these. But when you put that energy in, it lowers the temperature, right? It's absorbing that energy. So technically, the solvent-solvent attractions are greater than the solvent-solute attraction. But since heat is being put into the system, we are able to overcome that solvent attraction, and the ammonium nitrate will dissolve. Now, number 2, it says parts of the free response question. Let's keep going. It says A, a particulate representation of F2 is shown above in the formula of the equation below. Using the key provided, draw the particulate representations of CH4 in two products and molecules and the reaction above their formulas in the equation. So basically it's asking us to draw a particulate diagram. So for CH4, I draw a pretty big carbon, okay? And then I have 4 hydrogens. Now this is supposed to be black, but I'm just going to do dark gray. 4 hydrogens. So that's supposed to look like that. And then F2 is white. Now CH3, so we got the carbon. And then we're going to have our 3 hydrogens. And then we're going to have our 1 fluorine, which is going to be white. And then here, we're going to have hydrogen and fluorine bonded together like that. Okay. Now, this says use bond enthalpies in the table below to calculate the numerical estimate of delta H for the reaction. And so what that is going to do, what we're going to do for that is use the enthalpies of bonds broken minus the enthalpies of bonds formed. So delta H equals 413, which is the enthalpy of bond formed, 4 times 413, plus 155, okay, because there's 1 FF bond for our reactants, minus 3 times 413, because there's 3 CH bonds being formed, plus 485, because there's 1 CF bond being formed, plus 567, because there's 1 HF bond being formed. And so when we do that, we get negative 484 kilojoules per mole. Okay. Now it says C, the energy reactions are shown in the following energy diagram. On the right side of the energy diagram, draw a horizontal line segment to indicate the energy of the products. Draw a vertical double-headed arrow on the graph to correspond with the value of delta H for the reaction. So our delta H here was negative. So that means that it's an exothermic reaction. So remember, in our reaction, we're starting off here. We have to increase the energy before it decreases, okay? Now it's saying draw a horizontal line segment to indicate the energy of the products, which is here. And our products are CH3F and H2. Okay, so you want to label that. And then it says draw a vertical double-headed arrow on the graph to represent the delta H of the reaction. So remember, the delta H of the reaction is the amount of energy we get out of the reaction total. And so that energy is going to be 484 kilojoules per mole. Okay. Negative 484 kilojoules per mole. And so that's what your graph should look like. So that's the end of the progress check review.